I'm going to talk a little bit about crossing over and what happens when chromatids cross over and the result of that. So we know when we make our gametes, our sperm or eggs, during meiosis, our chromosomes, each homologous chromosome comes together with its partner, with its matching homologue from the other parent. So here we've got in blue a chromosome from mom and the matching chromosome that comes from dad, and they come together in a process called synapsis. Now when that happens, crossing over can occur. Sometimes it doesn't, sometimes it does. It's a pretty random thing. When they do cross over, it's literally what the name suggests. These two inner chromatids cross over, and when they do that, they can actually exchange pieces of DNA. So you can see that this blue section of this chromosome, this green chromosome, and this section of blue chromosome are actually trading places. So this chromosome that you got from your mom, when you pass it on to your offspring, you're actually passing it on with a little bit of DNA that you got from your dad. So it's mixing up your parents' chromosomes a little bit. Now it's important to note that genes that are close together are not separated because of crossing over very often. So we look at B and C here. These genes are not going to be separated by crossing over very often, because for that to happen, the two chromosomes would have to cross over right at that point. As opposed to anywhere along this whole chromosome, it would have to cross over right there. And that's not all that likely. Whereas genes A and B are quite a bit farther apart. So for these to be separated by crossing over, that crossover could happen in anywhere along that chromosome. And that's much more likely. Now we use this information to help us figure out distances on chromosome. So we know that chromosomes, or genes that are close together, don't cross over very often, and genes that are far apart do. So basically we can use that information. So the percentage of crossovers that we see in offspring, we use to measure distances. We call it map units. So we use map units to talk about distances on chromosome, not meters. And it just so happens that for every 1% crossover we see in the offspring, that equals 1 map unit. So if I do a cross and I see that 15% of the offspring are because of crossing over, I know those genes are 15 map units apart. Or 25% crossovers means 25 map units apart. Okay? So let's look at an example of a question you can get. Now I know it says given the cross in the previous slide. The previous slide is not important. But I've done a cross and I've got the genotypes and the numbers of each kind of genotype there. So remember, to figure out the distances between the genes, T and R, which is what the question is asking me to do, I have to figure out the percentage of crossovers, right? Because each percentage crossovers equals 1 map unit. So I need to figure out, of these 4 types, which ones are crossovers. Well, very simple. The smallest numbers are always the crossovers. So that's a crossover type, and that's a crossover type. And again, that's because crossing over is relatively random. It doesn't always happen. So they're always going to be the smallest numbers, the crossovers. The ones that are not crossovers, we call them parental types. Okay? So I know which ones are the crossovers, 33 and 42. So there are 33 and 42 individuals because of crossing over for a total of 75. 75 of those individuals are crossovers. And if I count them all up, I know there's a total of 280 individuals. So 75 out of 280, very easy to find a percentage there. 75 divided by 280. I get the percentage, and whatever that percentage is equals the number of map units that separate those two genes. Now here's another kind of question.
Zach Spencer, to the office immediately. Zach Spencer.
Here's another kind of question you could see. And this involves several genes on one chromosome. And it tells us the crossover distances between the various genes, and we have to use this information to draw a map of the chromosome. So when we have to draw a map of the chromosome, we can just draw a line. And that line represents the chromosome. Now, best strategy is always start with the genes that are closest together. So looking at these numbers, I can see the smallest percent crossover, and therefore the smallest number of map units is 1.5%. And that's genes W and F. So I'm going to put W there, and I'm going to put F there, and I know they are 1.5 map units apart. Okay, so now I'm going to figure out where one of the other genes fits in. I have to do this step by step. So let's figure out where E fits in. Well, it tells me that E and W are 4 map units apart. And how far from E is F? E and F are 2.5 map units apart. So I can see that E is closer to F than it is to W. So if I know E is closer to F, going back to my map, I know that E must be over here. So I'm going to put a little thing there, put E there, and I know that E and F are 2.5 map units apart. Now just to make sure I did this right, we know that W and E should be 1.5, 2.5, that's 4. So W and E should be 4 map units apart, and they are. Now we have to figure out where R fits in. So I have the distance between R and W, and I have the distance between R and F. R and W are 6 map units apart. R and F are 4.5 units. So again, R must be closer to F than it is to W. So on my map, if R is closer to F than W, R must be over here on this side. So it tells me that R and F are 4.5 map units. So I go 2.5 map units to E, and then a further 2 map units to get to R. And there is my chromosome map. Just lists the order of genes on the chromosome and the distances between them.